a simple but real problem, which is that of classifying handwritten digits. And for this, we can load the data in scikit-learn using sklearn.datasets.loadDigits. And so when we call this function, we will get the digits object. And what this data really is a set of many images of handwritten digits. And the task is to recognize the handwritten digit. So it's to predict whether the digit is 0, 1, 2, 3, etc. So is this a regression task or a classification task? Well, even though the output is numbers, this is a classification task because what matters is that I predict the correct digit and not that I predict close to the correct digit. So we have those pictures and we need to fit a classifier to them. So to do this, I am given images, digit.images, which are of dimension 64. There are dimension 8 by 8, and I can look at them, but I will need to feed them into the classifier. To look at them, unfortunately, I cannot visualize data points in a 64 dimension. So I can reduce the data using a principal component analysis. And for this, I will use another type of scikit-learn object, which is the principal component analysis. This object can transform the data by projecting it in a lower dimension. So I will take the 64 dimension data, and I will project it in 2 dimensions. And I can do this by creating the PCA object and then calling fit transform on it. And if I do this, I go from data that is of dimension 64 to data that is of dimension 2. And now that the data is of dimension 2, I can visualize it. So this is what I get. I get a cloud of points in dimension 2, and I have given a different color for each point. And what you can see here is that the points separate themselves. So given this representation, which number do you think the classifier might have trouble distinguishing? Basically, this question amounts to, where do I have a lot of overlap in those numbers? You can see that it's around here, for instance. So 1 seems to be hard to distinguish from 8, from 5. This is probably because some 8s are written in a very narrow way and some 5s are written in a very narrow way. However, it is important to keep in mind that the data is not only in those 2 dimensions that we're looking at, but is in a higher dimension. And we're going to give this complete dimension to the classifier. So the classifier may be able to find separations that we cannot see. So now that I've looked at this data, I will use simple models to try to build classification. And maybe the most simple um, classification model, classifier that I can use is the Gaussian naive Bayes. In scikit-learn, we can find it under sclearn.naivebayes.gaussian_nb. Okay? So what I will do is that I will import this model from scikit-learn, and then I will split my data into a train set and a test set. And the reason that I do this is because, as I mentioned before, I cannot judge the quality of prediction on data that I have used to train the model. So I have a question, which is, how does the democratization and the reproducibility of machine learning are combined? Democratization of machine learning, to me, is about putting machine learning in the hands of everybody. Reproducibility means that the outcomes, whether they're a model that predicts or a finding on the model that predicts, are trustworthy. And the question is, how important are these? And in my opinion, they are very important because machine learning has a huge potential. Machine learning can change many things in people's life. And so we need to make it easier for people to understand machine learning and to build things themselves with machine learning. And this is one of the goals of scikit-learn, is to make it easy for people to build things themselves. And this is maybe what I'm trying to illustrate today. So to go back to my example, we're trying to build a classifier that separates digits. And for this, we're using the simplest possible classifier, which is the Gaussian naive Bayes. And we're splitting the data in train and test set. And for this, we're going to use the train test split to separate X train, X test, Y train, and Y test. And now we can fit the model. So we're going to create the Gaussian naive Bayes object, and we are going to fit it on the data, so X train and Y train, and we can predict on left out data. And then we can compare our prediction to the expected labels, and we can quantify the error. Okay, so here I am plotting the data and the predicted label, and I'm using different colors. Green means the prediction was correct. Red means the prediction was incorrect. So here you see an example of incorrect prediction, where if I look at the data, it looks like a 9, but the classifier predicted an 8. Okay? So it's important to keep in mind that we need to split the data in train and validation sets, train and test set, to be able to properly measure our prediction accuracy by looking at the difference between the predicted labels and the actual labels. So I have a question on the PCA step above, and the question is, we've reduced the data to go from 64 dimensions to 2 dimensions. How do we know that the 2 chosen dimensions are the most representative of the problem? Well, The PCA knows nothing about why. It's called an unsupervised learning method. So it can't do an informed choice with regards to why. So what it does is it takes the axis of the data that capture the most variance. This is the criterion of the PCA. It tries to capture the most variance. However, variance may not be the most useful information. So PCA does not give us any other guarantees than capturing variance. It is still quite useful in general. So I've shown you how we can apply a very simple model to data to get a prediction. One thing that I forgot to tell you is that although those are images and they're 2D, each sample in scikit-learn is 1D. So we have flattened those images. This is how we get 64 dimensions. So now that we have such a prediction, we can measure the performance quantitatively. We can do this in a naive way by simply counting the number of times we got it wrong. And here we see that this naive-based classifier got a correct answer more than 80% of the time. So there are other ways of measuring the error, and in general, in scikit-learn, they're found in this clearn.metrics submodule. And one very useful metric is the classification report, which combines several measures to print a table with the result. So if I take my expected labels and my predicted labels, I can print the corresponding classification report. And what I get is for each class, I get a measure of precision. So what fraction of the detections in this class were correct detections? The recall, what fraction of this class did the classifier get right? So for the class 0, all the predicted zeros were actual zeros because I have a precision of 1. However, the classifier found only 91% of the zeros. The F1 score is a combination of those two metrics, and the higher it is, the better. And the support is the number of zeros that were in the test set. So this gives me a complete view of the error per class. And here I have 10 classes. I can also look at the confusion matrix. So I can print it using metrics.confusion matrix. And this tells me what 0, so the first class is 0, to which class it is confused. So 0 is confused to 1, 2, 3, 4. 0, the classifier mistakes some zeros to 4s, some zeros to 5, 6, 7, etc. And in particular, we can see that number 1, which is here, is often being labeled number 8, which is here, okay? Which corresponds with the intuitions that we had developed earlier looking at the two-dimensional embedding. So this was an example of a classification task. I want to stress that we used an extremely simple model, the naive Bayes, and it's really the simplest model. We can use more elaborate models, and I will detail them a bit. I have a question that is asking me what makes the naive Bayes naive. So it's called a naive Bayes because it models each features independently. It doesn't capture well the relationship between features. In general, this is a limitation. However, it enables it to be very fast, and also it is a regularization, so it is a very simple model that is less likely to overfit. I will cover later how we can compare different models to be able to choose the best one.